In this work, we focus on the task of semi-supervised node classification on heterophilic graphs. We are given a graph with feature vectors associated with each node and a few label nodes. We focus on the transductive setting where the feature vectors are made available for all the nodes. In the recent years, graph neural networks have shown to be effective for this task. Graph neural networks leverage network information along with node features to improve the semi-supervised classification performance. However, many GNNs rely on the similarity of connected nodes. Several GNNs perform poorly on graphs that violate this assumption. Homomorphic graphs exhibit this phenomenon where for any given node, majority of the neighbors belong to the same class. However, there are several graphs that exhibit the opposite behavior. In heterophilic graphs, majority of the neighbors belong to different classes. Several GNN architectures were proposed in the recent literature to deal with heterophilic graphs. These contributions can be grouped into three categories. The first class of models modify the neighborhood aggregation scheme. Some examples of the models that belong to this class include geometric GCN, H2GCN, and SuperCat. The second class of models explicitly model the label compatibility matrix for modeling heterophily levels in the input graph. CPGNN falls under this category. The final class of models design graph filters to capture high-frequency, low-frequency components useful for the task. Examples include FAGCN and GPRGNN. Our work is closely connected to GPRGNN. Our contributions can be summarized as follows. GPRGNN can be interpreted as adapting eigenvalues of the input graph to leverage useful signals from the eigenspectrum to improve task performance. We dig deeper to empirically analyze eigenvalue spectrum of the heterophilic graphs. Following our analysis, we design a simple aggregation model for heterophilic graphs. We finally proposed an alternative approach that can address the shortcomings of the aggregation model for heterophily. To further understand heterophilic graphs, we conduct the following experiment to empirically analyze which eigenvalues are important in heterophilic settings. We directly work with the graph that is symmetric normalized with self-edges. We consider the eigendecomposition of the given graph as A equals U sigma U transpose, and we assign the node features as U root sigma. We construct new training data with these features using the known labels from training set. A logistic regression model is trained on this data. We plot the per class weights learned by the model. The weights serve as a proxy for importance of eigenvectors. The x-axis is the index of the eigenvalues sorted in descending order, and the y-axis denotes the weight assigned to the corresponding eigenvector. These weights give the importance of eigenvectors. These plots show the spread of useful signals across the spectrum. For instance, the chameleon and squirrel datasets exhibit a dumbbell-like distribution. The two extremes of the spectrum have high absolute weights, suggesting that selecting these eigenvectors can improve performance on heterophilic graphs. The relation between eigenvalues and singular values is well known from the matrix algebra. In Figure 1a, we plot the eigenvalue spectrum for the chameleon dataset. The x-axis corresponds to eigenvalue index, and the y-axis signifies the eigenvalue strength. Eigendecomposition naturally induces negative values. In Figure 1b, we plot the absolute eigenvalue spectrum, and in Figure 1c, we plot the singular value spectrum for the chameleon dataset. The absolute eigenvalues spectrum plot is similar to the singular value spectrum. Therefore, selecting top case singular values can capture components from both ends of the spectrum. This suggests that replacing an input graph with truncated singular value decomposition of the input graph in aggregation scheme might perform better. Neighborhood aggregation is defined as A hat X, where A hat is the symmetric normalized graph. Following our insight, we replace the input graph A hat with the TSVD approximation of A hat. The same idea can be applied and extended to node features. Several text classification literature showed the benefits of applying PCA to input features, especially on bag-of-word input features. Therefore, in our final formulation, we apply TSVD on the input graph and PCA on node features. The aggregated feature output is then sent to a logistic regression classifier. Varying TSVD dimensions K1 and K2 show improvements in performance, which we later show during the experiments discussion. In our experiments, the parameters K1 and K2 are treated as hyperparameters. We conduct experiments on 7 heterophilic datasets that are publicly available. The homophily levels in these datasets ranges from 11% to 30%, indicating they are highly heterophilic in nature. All aggregation-based benchmark models prescribe to apply symmetric normalization to the input graph. Therefore, for a fair comparison, we use symmetric normalization in our TSVD aggregation model. We present the results for our TSVD aggregation model in this table. TSVD aggregation model outperforms popular aggregation-based models like GCN, SDCN on several datasets. We observe gains in performance of up to 10 percentage points. TSVD aggregation model outperforms or performs competitively against aggregation-based models like SuperGAT and geometric GCN, which were proposed to primarily address heterophily. In this comparison, we observed gains of up to 18 percentage points. On comparison with GPR-GNN, the state-of-the-art model, our proposed model outperforms GPR-GNN on squirrel, chameleon, and crocodile dataset, though lacking on other datasets. For Texas, Wisconsin, and Cornell datasets, we observe node features are rich in information, but aggregation models that solely rely on aggregated features tend to suffer. We will address this shortly. Graph normalization plays a role in classification performance for heterophilic datasets. To study this, we treat graph normalization as a hyperparameter and sweep in set, no normalization, row normalization, and symmetric normalization. We observe significant performance improvements in general by varying graph normalization scheme. Massive gains of up to 17 percentage points are observed on the squirrel and chameleon datasets. Several neighborhood aggregation models performed poorly on datasets with informative features. This poor performance could be a result of incompatibility between the input graph and the node features. Several models that were proposed to tackle heterophily still operate in the aggregation world. Idiomatically, these models may be trying to treat the symptoms rather than fix the cause. Can we decouple the disparity between the graph and features caused by neighborhood aggregation? The input graph and node features are two sources of information. There are datasets like Texas, Wisconsin, and Cornell, where the node features are informative. Contrastingly, there are datasets like squirrel, chameleon, and crocodile, where the input features contains useful signals. Ideally, features can be constructed from both these sources and then fused. A simple way to fuse is to use concatenation. In our proposed TSVD concat model, we extract features from the input graph and node features by applying truncated singular value decomposition. Parameters K1 and K2 control the amount of signals to be extracted from each source. Concatenation can also eliminate the incompatibility between input graph and the node features. The benefits of this model can be observed in our upcoming evaluation section. Models that do not use the input graph perform better on several heterophilic datasets like Texas, Wisconsin, and Cornell when the node features are informative, while the models that solely rely on aggregated features tend to perform poorly. This suggests that there is some incompatibility between node features and the input graph that is not well understood, and simple aggregation mechanisms are insufficient. To highlight this aspect, we proposed the TSVD concat model. As hypothesized, the concat model can leverage the discriminating features from both the graph and feature space, and thereby improve performance beyond the MLP classifier. We also observe that the concat model performs competitively or better on remaining datasets. On comparing TSVD concat model with the benchmark aggregation models, we observe gains of up to 30 percentage points with our proposed concat model. In this section, we will compare concatenation and aggregation models. The maximum gains for the TSVD concat model is achieved on the squirrel and chameleon datasets, where a dumbbell-shaped behavior is observed for the weights assigned to eigenvectors. By varying the dimensions in TSVD, the concat model is able to find the optimal set of signals from both extremes of the eigenspectrum to improve the performance for the given task. We can notice that TSVD aggregation model also performs competitively. Hence, these gains can be attributed to tuning the K1, K2 parameters that control the dimensions of TSVD decomposition. On Texas, Wisconsin, and the Cornell datasets, where the input features are informative, the improvements in TSVD concat model can be attributed to discriminating features coming from the graph features. The TSVD concat model, by being unaffected by incompatibility between nodes features and graph features, can outperform TSVD aggregation model. To study the effect of tuning TSVD dimensions, we conduct an ablative study. In the first setting, we restrict the TSVD dimensions and report the test accuracy. In the second setting, we tune the TSVD dimensions parameters K1 and K2 and report the test accuracy. We observe gains of up to 12% by tuning the TSVD dimensions, suggesting the importance of tuning K. Even in concat models, which decouples input features and graph features, tuning K1, K2 can help eliminate noise in the source features and thus improve generalization. Next, we compare learned embeddings for the best benchmark models against our TSVD concat model on the Squirrel dataset. To qualitatively evaluate the learned embeddings, we show the t-SNE plots of the learned embeddings for GPRGNN and a proposed TSVD concat model. The class clusters in GPRGNN's t-SNE plot are mixed, while our concat model shows clean, discernible clusters. We summarize the several points we touched upon in this talk here. Carefully analyzing these nuances might help us uncover a robust model that can work across the spectrum.